Think of the DNS namespace like a giant family tree. At the very top is the root, which is just a dot. Below it are big branches called top-level domains, abbreviated TLDS, such as .com, .org.uk. Each top-level domain is split into second-level names, for example .com and mischool.org, and can be split again, like sub.example.com. This is called a hierarchical namespace because every name is built from parent pieces, just like a street address: house, street, city, country. A zone is the part of that tree that a single DNS server is responsible for. The server holds all the records for its zone and tells the world, "I know everything about example.com, but for anything under .com I will ask my parent server." This handing off is zone delegation. Imagine a manager giving a team its own to-do list while still reporting to a higher manager. Delegation is recorded with NS records, standing for name server records, that point to the servers that own the child zone. A DNS resolver is the helper that turns a human-readable name, like www.fun.com, into an IP address. Stub resolver. This lives inside your computer or phone. It knows only two things: the address of a recursive resolver, often provided by your ISP, and how to ask it a question. It's like a child asking a parent for help. Recursive resolver. This works for many clients. It receives the question and then does the whole hunt itself, walking from the root down to the authoritative server, caching answers along the way. It's the diligent librarian who finds the exact book you need. Forwarding resolver. Instead of doing the full hunt, it forwards the request to another resolver, maybe a corporate DNS server, and returns the answer. Think of it as a teenager who asks an older sibling to fetch something from the store. Each type balances workload and control. Stub resolvers are light, recursive resolvers do the heavy lifting, and forwarders let organizations apply custom policies. When a client asks for a name, the DNS system can work in two ways. Iterative non-recursive resolution. The resolver asks one server, gets a referral to the next server, then asks that server, and so on. The client or resolver does the walking. It's like a treasure hunt where you receive a clue at each step. Go ask the librarian at the next floor. Recursive resolution. The client asks one server to give the final answer. That server does the whole walk for you, returning the final IP address. It's like telling a friend to fetch a book for you. They go through all the shelves and bring it back. Step-by-step recursive flow. Step 1. Resolver sends query to root server. Step 2. Root replies with name server records for the top-level domain, for example com. Step 3. Resolver queries a com server, gets name server records, for example .com. Step 4. Resolver queries the authoritative server, for example .com, and finally receives the A or AAAA record. In iterative mode, the client would repeat steps 2 to 4 itself, using each referral in turn. Both modes use the same DNS message format, only the behavior differs. DNS stores many types of information, each called a resource record RR. Think of each RR as a sticky note with a label and a value. A holds an IPv4 address 93.184.216.34, format 4 bytes. A AAA holds an IPv6 address 2606:280:220.1:248:1:893:258:11946, format 16 bytes. CNAME canonical name says this name is an alias for another name. Value is another domain name. MX Mail Exchange tells mail servers where to deliver email. Contains a priority number 16-bit and a host name. SRV service record used for protocols like SIP or Minecraft. Holds priority wait port and target host name. TXT freeform text often used for verification strings or SPF policies. NS name server points to the authoritative server for a zone. Value is a host name. SO a start of authority appears once per zone and contains several fields: primary, NS responsible mailbox serial number, refresh, retry, expire. And minimum TTL, it looks like SO a ns1.example.com, hostmaster.example.com, 202401010172000363600 120960036000. Each record also carries a TTL time to live that tells how long a resolver may keep it in cache before asking again. Explanation: when a resolver gets an answer, it caches it for a period called TTL time to live. The cache works like a sticky note on your fridge. You keep it until the date on the note expires. TTL computation: if the TTL is 3,600 seconds, the resolver will keep the record for 1 hour. When the timer runs out, the entry is discarded or refreshed. Exponential backoff is used when a query fails. For example, the server is unreachable. The resolver waits longer each retry to avoid flooding the network. The wait time W after the NTH failure is W sub n equals the minimum of base times 2 to the power of n-1, and max backoff, where base might be 1 second and max backoff could be 30 seconds. For example, first retry 1 second, second retry 2 seconds, third retry 4 seconds, fourth retry 8 seconds, and so on until it caps at the maximum. This math reduces traffic while still giving the server chances to recover. Resolvers also use negative caching. If a name does not exist, NXDOMAN, they cache that negative answer for the minimum TTL defined in the SOA record, usually 300 seconds, so they do not keep asking the same question repeatedly. Load balancing in DNS decides which IP address to give back when several exist for the same name. Imagine a playground with several swings. The supervisor decides which child gets which swing. Round robin, the DNS server cycles through the list of IPs in order, returning the next one each time. If there are 3 IPs A, B, C, the first query gets A, the second B, the third C, the fourth A again, and so on. Simple, but treats each server equally. Weighted round robin, each IP gets a weight W sub I. For example, A equals 5, B equals 2, C equals 1. The server returns each address proportionally to its weight. Mathematically, the probability P sub I of returning IPI is P sub I equals W sub I divided by sigma W sub J. So it gets 5/8 of the traffic, B 2/8, C 1/8. Geolocation-based selection, the resolver looks at the client's IP and chooses the server that is closest. Often a hash function maps the client's IP to a region, then selects the nearest record. A common hash is FNV1 or simple modulo. Region equals client IP modulo n_regions. These techniques can be combined. For example, first pick a region, then apply weighted round robin within that region. The goal is to spread load and reduce latency for users. DNSSEC adds a layer of digital signatures to DNS records, so you can be sure the answer didn't get changed by a bad guy. Chain of trust, the root zone is signed with a root key. KSK, each top-level domain signs its own zone with a ZSK zone signing key and publishes a DS record delegation signer that points back to the root's key. This continues down. Example.com zone is signed, its DS points to .com ZSK, and so on. Think of it like a row of trusted witnesses, each vouching for the next. Signature verification mathematics. DNSSEC uses public key cryptography, typically RSA or ECDSA for a record R. The signer computes a hash H equals hash of R, using SHA-256 for RSA SHA-256. Then it encrypts the hash with its private key to create a signature S equals enc private of H. The signer obtains the public key K public from the zone's DNSKEY record and verifies. H prime equals dec public of S, except if H prime equals H. Key rollover, to keep security strong, keys are periodically changed. The KSK signs the DNSKEY set, including the new ZSK, while the old ZSK may still be valid for a grace period. In practice, a resolver validates the entire chain from root to the answer. If any link is missing or the signatures don't verify, the answer is considered bogus. UDP- the default. It's fast because it's connectionless, but each DNS packet must fit in a single UDP datagram, original limit 512 bytes. If a response is larger, the server sets the TC, truncated flag, and the client retries over TCP. TCP- used for zone transfers, a XFR, IXFR, and for large responses. It establishes a three-way handshake guaranteeing ordered delivery. EDNS0, extension mechanisms for DNS0, is an optional extension that lets clients advertise a larger UDP payload size up to 4096 bytes and carry extra options like DNSSEC records. It works by adding an OPT pseudo RR in the additional section. Example: A client sends UDP payload size equals 4096. The server can now respond with bigger answers without switching to TCP. Message size limits matter because a DNS response may contain many records, for example all AAA, NS, and DNS-SEC signatures. If the size exceeds the advertised limit, the server again sets the TC flag, prompting TCP fallback. Query latency, the time from sending a query to receiving a reply, measured in milliseconds. Average latency, L bar, can be computed as L bar equals the sum from I equals 1 to n of latency I divided by n. A high L bar may indicate network congestion or an overloaded resolver. Cache hit ratio, the proportion of queries answered from cache versus those that required a full lookup. If H is the number of hits and M the total queries, hit ratio equals H divided by M. A hit ratio above 80% is typically good. It reduces traffic to upstream servers. Statistical modeling, traffic, often follows a Pareto 80-20 distribution. A few popular names generate most queries. Operators use Poisson processes to model arrival rates, lambda, and exponential distributions for inter-arrival times. The probability of k queries in interval t is P of k given lambda t equals e to the minus lambda t times lambda t to the k divided by k factorial. Understanding these patterns helps size caches and predict load spikes. Other useful metrics: error rate, NXDOMAIN, SCRVFAIL, number of retransmissions, and the distribution of response codes, RCODE. Monitoring tools, for example Prometheus exporters, Grafana dashboards, plot these values over time, allowing operators to spot anomalies before users notice them.